Hi guys, Assalamu alaikum. Today we're gonna talk about the conjugate beam method, and actually it's one of my favorite methods, and probably 80% of engineers like to use that as well. I think in my opinion, it's a better method than the moment area method, and we will see how this method goes. So first of all, let's start off with an example. We remember this beam. We used that using the moment area method. We found theta b to be equal to WL cubed over 6EI, and we found the deflection equal to WL to the fourth divided by 8EI. Now, if I take this beam right here, this cantilever, and I'm just drawing the bending moment diagram for that. Okay, so here I have the M over EI diagram. So let's assume that I'm going to remove the fixed end here and make that as a free end. And then the free end over here, I'm going to transform that into a fixed end. Okay. And then I'm going to drop the moment diagram. And I'm going to assume now that this is my loading on this beam right here. So what have we done so far is as follows. We removed this fixed end and converted it to a free end over here. And we took this free end and convert that to a fixed end over here. Okay. Now, then we drop the moment diagram, and we assume that this is now the load on this beam that we just made up. Okay, so we made up this beam. This beam does not exist. All right. Now you've noticed that the arrows are going away from the beam, and since I'm drawing on the tension side, then usually the load or the direction of the load in my way is always away from the beam. Okay. So now for this beam, can I find the reaction? Of course I can. Okay. I can find the moment at B, and I also can find the shear or the reaction at B. To find the reaction at B, or VB, for instance, or sometimes I call it BY, I'm just going to use the equilibrium equation, and I'm going to say that's a summation in y direction is equal to 0. Then, because this is a second degree, then the area is going to be 1/3 the length L times the height, which is WL squared over 2EI, minus VB equal to 0. Then VB is equal to WL cubed over 6EI. And that looks exactly like theta B. Okay, so you'll get back to that. Moving on, let's find the moment about B to get MB, and I'm going to assume that as my positive direction. Then again, using that load over here, it's going to be the area under this diagram, which is going to be 1/3 times L times WL squared over 2EI times the moment about B, which is 3/4 of L, minus MB equal to 0. Then MB is equal to WL4 over 8EI. Again, look at the delta B that we had before. So for this beam that now I'm going to call the conjugate beam, and the conjugate beam, again, it's a fictitious beam. That beam does not exist. We just made it up. Okay? We found for that beam, which I'm going to call the conjugate beam, that the angle of rotation in the real beam, again, this being the real beam, is the same as the shear of the conjugate beam, and that the deflection of the real beam is the same as the moment of the conjugate beam. Okay, so if I want to put that in the statement, then theta B for the real beam is equal to the shear at B for the conjugate beam. Again, conjugate means made up. Delta B, which is the deflection in the real beam, is equal to the moment of the conjugate beam. Okay, so from that we can conclude that the internal forces in the conjugate beam is equal to the deflection in the real beam, providing the support conditions on the next slide. Okay, providing the support, and I think I dropped that condition. Just add this Okay, the support conditions on the next slide. Okay, so what's happening here? So you've noticed that, or we know that the slope of the shear diagram dv by dx is actually equal to the load, right? So if I wanted the shear, I just integrate the load. And we also noticed from the moment area diagram, or for strength of material, that the change in the angle, or theta, is equal m over ei. So if I want theta, then this is also the integration of m over ei dx. So hence we notice the analogy between the shear and the angle. For the same thing, if we take the second derivative for the moment, dm squared by dx squared, this is also is equal to load. And we know from strength of material that the change, or the second derivative of the deflection, here v, small v is the deflection, is also equal m over ei. So if I want m, then this is a double integration of the load, and then the vertical deflection is also the double integration of m over ei. Hence, again, the analogy, and that's how this technique actually came about. Before I move on to the support condition, I just want to talk about the sign convention. So if I have a positive shear, then my theta rotation is clockwise. If I have a positive moment, then delta is assumed to be downward. Again, this is because I'm drawing on the tension side. Okay, my positive is, let me write this, tension side. Okay, so if I'm drawing my moment diagram on the tension side, then the loads are going to be away from the beam. Positive shear on the conjugate beam means my theta is rotating clockwise. Positive moment means that my deflection is downward. Okay, now I'm going to talk about the support conditions. So here, if I have what I call the real beam, and here is the conjugate beam. So the type of support, if I have a simple end support, like a hinge, like so, or a roller, we know that theta here is not equal to 0. And we know here that delta is equal to 0. Okay, so I still would like to keep the same condition in the conjugate beam, meaning if my moment, or if my deflection is equal to 0, and since the deflection is analogous to my moment, then my moment must also be equal to 0 in the conjugate beam. Theta is not equal to 0, which means that the shear is not equal to 0 as well. Okay, so the type of support is the same basically between the conjugate and real beam if these are the end supports, because here I have a reaction and the moment here is equal to 0, so my deflection is equal to 0. So this represents my theta now, and this also represents my theta, which is again my shear. If I go to the fixed support, I know I have both theta equal to 0 and the deflection equal to 0. So as a consequence, in the conjugate beam, I need to simulate a position where my shear is also equal to 0 and my moment is also equal to 0 for me to be able to satisfy this. And this is only applicable through being at the free end, because I know at the free end here, this is my free end right here, I know that my shear is equal to 0 and my moment is equal to 0 because I don't have any loading in this direction. So again, so this is real beam going through for the conjugate beam. Now, if I have a free end, okay, so the deflection is not equal to 0, as we proved in previous examples, and delta is not equal to 0 as well, okay? Which means in the conjugate beam, I need this theta, which is analogous to my shear. This should not be equal to 0 as well, and then my moment is not equal to 0 as well, which means my free end becomes now a fixed support, okay? So good so far. So what we have done so far, that a simple end support, whether it's a hinge or a roller, it's the same in the conjugate beam. If I have fixed support in the real beam, it becomes free in the conjugate. If I have a free end in the real beam, it becomes fixed in the conjugate beam. Now we're moving on to the simple interior supports. Now, as far as interior supports are going like this, still theta is not equal to 0 because we have an angle of rotation there, but we don't have any deflection. Okay, so I need a position in which my shear is not equal to 0, so there's a value for the shear, but my moment is equal to 0, and that's usually represented by the internal hinge. We know at the internal hinge, moments are equal to 0 always, but the shear is not. Okay, so again, real beam, interior support gives me internal hinge. Now, if I have an internal hinge in the real beam, okay, then again, theta here is not equal to 0, and we know that, and delta is not equal to 0. So at this case, I need something where the shear is not equal to 0 and the moment is not equal to 0, and that happens when I have a simple interior support. Okay, and I will show you how we are going to utilize these support conditions when we solve the examples. A question might arise here. Well, one thing I want to point out, if I have a statically determinant beam or real beam, then the conjugate beam is also going to be statically determinant and stable. Okay, that's a one-to-one correlation. For the indeterminate beams, that's another matter. By the way, we can use the conjugate beam for indeterminate beams as well, if you want to. If we know what the moment diagram is, then we can simply find the deflections any point we want. There's one thing that might arise though. So let's say I have this indeterminate beam, and if I want to convert that into a conjugate beam, so here's real, and here is conjugate. Okay, don't want you to confuse the two. So now this becomes an internal hinge, this becomes an internal hinge, and this stays as is. So the one thing that you might say, hey, but wait a minute, isn't that unstable? And I would say technically it is unstable, but since there is an equilibrium condition between my conjugate beam and the applied load, and remember this load is your M over EI diagram, then here the stability or instability really doesn't matter, and we are only using this. Again, remember that the conjugate beam is not a real beam, it's a fictitious made-up beam, although it looks like it is unstable, but because it is under equilibrium with the moment over EI diagram, it's not an issue for us. Okay, but again, since here in this course or this class in particular, we are only dealing with statically determinate beams, so this is really not an issue for us at all. So I'm going to start off with example number 1, and I'm going to use the same example that we used for the moment area methods so that we can compare the results of the two. So here I have again the load, which is 100 kilonewton. Here's my real beam. Okay, so I'm going to simply now drop this right here as is. Now again, since this is an end support A and end support B, so they are going to be the same for my conjugate beam right here. All right. My moment diagram, again, it's going to be P times AB over L, which is 100 times 4 times 6 divided by 10, which is going to give me my 240 EI. So this is going to be my moment diagram. So to convert, again, now to convert this loading, again, since I'm drawing on the tension side, the load is away from the beam, as you can see, away from the beam, okay, away from the beam. So now this is my conjugate beam right there. So the conjugate beam is just technically a beam with modified support conditions under the loading of the moment diagram. So now, again, now I'm going to find, as you hear, I really don't need to find the reaction. No need to find the reaction for this beam at all, since I was able to draw my moment diagram. So now I'm going to find the reaction for this beam, because I'm going to need that to find what he's asking me of, which is my theta C and delta C. So here, first I'm going to take the summation of moment about B is equal to 0. Then RA, which is this one, times the distance 10 minus now 1/2 times 4 times 240 over EI times 4 over 3, because here is the location of my centroid, okay, plus this distance, which is 6. So this is the moment arm, minus this triangle now, 1/2 times 6 times 240 over EI times 2/3 over 6 is equal to 0. From that, I was able to find RA equal to 640 over EI, which is, by the way, my theta A, which is what we found also in the moment area method. So now to get to what I really want, which is my theta C and delta C, I'm going to take a cut section. So I'm taking a section at C. Okay. Here is my reaction, 640 over EI. At C, I have the moment of 240 over EI, and this distance was 4 meters. To find theta C, or shear at C, I'm just going to use the equilibrium equation. Summation of Fy is equal to 0. Then 640 over EI minus 1/2 times 4 times, again, because this is now that force over here, minus Vc is equal to 0. Then Vc is equal to theta C, which is 160 over EI. Since I have a positive shear, then the rotation of this angle is clockwise, and we got the same result as the moment area method. But again, it's a little bit simpler because I really don't have to know what the deflected shape looks like. Now, to find the moment, I'm going to take the moment about C, just to be sure we have everything that we need. This is MC and this is VC. So taking the moment about C is equal to 0, then 640 over EI times 4 minus 1/2 times 4 times 140 over EI, again, which is this right there, times the moment arm 4/3 minus MC equal to 0. Then MC is equal to delta C, which is equal 1920 over EI. Again, positive moment, so the deflection is downward, and we got the same exact result as we did for the moment area method. Okay, so simply I'm just converting my real beam into a conjugate beam, and then we are getting the deflections, or the internal shear moment, which are my deflections and rotations. Let's have another example. This one here, again, I'm doing another example from the moment area method just to show you the difference between the two methods. And you can pick and choose, I guess, which one is easiest for you. But again, for me, conjugate beam is a lot simpler and a lot better to work with. Again, my opinion. All right. So here I have this beam, the same beam as before, 40 kilonewtons. Let me start off by drawing the moment diagram for this, and we did that before. Again, this 100, as a reminder, this 140 over EI is just simply your 70 times 2. Okay, so I probably need to put these just to make it clear. Okay. Again, then, so this is now my 140 over EI. Again, I'm here, my moment is equal to 0, so I'm just using this line, and then I'm superimposing the 40 kilonewton per meter, or WL square over 8, which is my 125 over EI. So this is now my moment diagram. Again, the loading is going to be away from the beam, though. So this is away from the beam and away from the beam. So let's talk about the reaction, the support conditions. So as far as A is concerned, since this is an internal, this is an end support, then this is probably going to be the same. A is going to be the same here. Okay. B now is an interior support, so this probably here is going to be an internal hinge. This is free, so this becomes fixed. So this is the fixed part. This is now the internal hinge, and this is the support. So this is now my conjugate beam. Okay. Still determinant. But here I'm probably going to need to find, again, what he wants, the theta C or delta C, right? So in this case, I need to find the reactions first at A. So here's my RA, here is my RC, and here is my C. All right. You could tell me why not start this part right here. Then the problem is here in this case I would have two equations with two unknowns, so why would I do that? I probably will start with the left part. Okay, take the moment about b is equal to 0, so because I don't like to solve simultaneous equations. Then 5RA, okay, plus 1/2 times 5 times 140 over EI times 5 over 3, again about point B, this is being my moment arm, minus 2/3, this is a full parabola, times 5 times 125 over EI times 2.5 is equal to 0. Then my RA, which is theta A, is equal to 91.667 over EI, and we got the same result as before. Now I'm going to take the whole beam and take the summation of Fy is equal to 0. By doing so, I can find RC directly, which is 91.67 EI. Again, up is positive, plus 1/2 times 7, which is this full triangle, okay, this full triangle right here, times 140 over EI, minus 2/3 times 5 times 125. So this is going to be my force this way, and this is going to be that force over here. Minus RC is equal to 0, then RC is equal to 165 over EI. Again, here I'm having negative shear, so this rotation is going to be clockwise. No, I mean positive shear, so this rotation is clockwise. Okay. So now I can take the right part, since the only unknown here is MC. So here I'm going to take the moment about B is equal to 0. This is going to be minus MC. Again, this is positive direction. This is minus MC minus 1/2 times 2 times 2 times 140 over EI times 2/3 plus 165 over EI times 2, which is this one right there. So MC is equal to 236.67 over EI, and since it is a positive moment, then delta C is pointing downward as before. Okay, and if I wanted to find theta B, which he is not asking for, but again, since I already did the full-blown example on moment area method, this is just to show you that I'm getting the same values as well. So I hope that was clear enough. I'm gonna, by the way, for this particular example, I asked for the maximum deflection. I'm not going to ask it here, but probably I might provide that in a separate video, because it's going to take a little bit more time to find that. But it's easier than, well, you be the judge when I do it for you, than finding the maximum moment using the moment area. So now I have another example, which is going to be the last example. Here I want you to find theta B, theta C, and delta B. Okay. Now, for this case, again, I'm going to draw the moment diagram. Well, here I need to find the reaction at C. Then I took the right part, took the moment about B equal to 0. This is being the positive. Then minus 6 RC minus 60 times 3, then RC is equal to 30 kilonewton. Now I'm going to take the whole beam to find the moment at A. And again, take this positive. This is equal to minus 12 times 30, which is this one, plus 60, which is my load, times 9 minus MA equal to 0, then MA is equal to 180 kilonewton meter, which is this right here. So if you've noticed, here I only needed to find RC at the moment at A, which was enough for me to draw the moment diagram. So now I'm going to convert that into the conjugate beam. Again, my loads are away from the beam and away from the beam. This internal hinge became an interior support. This fixed end here became free. Again, this interior became interior support, internal hinge. Simple is the same. Okay. Now, let's start finding let's find the theta c first of all. So for that, I'm going to take the summation of moment about b is equal to 0, and I'm going to have this as my positive direction. Then 6, which is these 3 plus 3 RC, minus this triangle over here, which is 1/2 times 1/2 times 90 over EI times 6 times 3, which is the moment arm, minus this triangle over here. Again, here this force is going to be like this, and that force is going to be like that. Actually, since this is going to be smack in the middle, I'll take this out. Yes, it's going to be right down in the middle. Okay, so I'm taking the moment again about point B right there. So from it, I find RC, which is the same as theta C, which is equal to 495 over EI. And since this is negative shear now, the rotation is going to be counterclockwise. Now, here I'm left with finding the reaction at B. I'm going to make summation of Fy equal to 0. Then RB is going to be equal to minus 165 over EI. Here I'm just using RB plus this reaction that I found right here, plus 1/2 times 6 times 180 minus 1/2 times 6 times 90. It's going to beat me out. Now the question is, does that represent the angle of rotation at B? Okay, and the answer to that is no. All right, I might call it a relative relative rotation, but you'll see what I mean in the next slide. So now here I divvied up the beam into 3 parts. So this is now the left part here. This is what's happening at the reaction, and this is the right part. All right. Now, if I take the left part by itself, I mean this one, I can, right? So here I have the moment at B and the shear at B, and I'm calling that shear B left. So now taking the moment at B equal to 0, then I have 1/2 times 180 over EI times 6 times 2/3 of 6 minus MB equal to 0. Then MB equal delta B, which is equal to 2160 over EI. Okay, so now I found the deflection at B. So using the equilibrium equations, now here I have the 765 EI that I found from the previous slide. Here I have, just skipped step, which is using for this part right here, the summation of Fy equal to 0. Then from that I can find VB left, and VB left is equal to 540 over EI, which is this guy right here. So this is pointing downward, so this is pointing upward. Now if I do summation of Fy for this part here, okay, another summation of Fy, then I can find VB, what I'm calling VB right. And that is simply 765 over EI minus 540 over EI, and that's going to be equal to 225 over EI. Okay, so if in the future, if I'm asking you for the rotation at an interior, and we know that from the beginning of the semester, that usually for an interior hinge, the angles are not equal. Okay, so theta 1 is not equal to theta 2, which we have right here, VB left and VB right. So for that, theta B left is going to be 540 EI clockwise, because here I have positive shear. Okay, this is positive shear. Theta B right, on the other hand, at 225 is counterclockwise, because here I have negative shear. Okay, now this part, the right part, here I can use that as a check. If I take the moment about B equals 0, I can find MB, which is going to be 2160 over EI, and I can find again also VB right, which is also going to give me 225 over EI. Okay, and this will end the conjugate beam method. Again, you guys, if you have any questions, feel free to email me, or actually when we're going to have one of these live classes, we're going to talk about that as well. So you guys stay safe and enjoy the rest of the day.